Hello and welcome back to our discussion about action potentials. In this section of our lectures, we're going to be talking about the ion channels that underlie the action potential. We're going to be answering these questions here. What are the characteristics of voltage-gated sodium and potassium channels? And how do these properties underlie the events of the action potential? All right, so I want to start off by reminding you that these phases of the action potential, these changes in membrane potential that occur during the action potential, are due to changes in permeability of the membrane to our two main ions that we're focusing on here, sodium and potassium. I would like to draw your attention to this plot right here, which shows the membrane voltage, the membrane potential in this dotted line, okay? And what you can see overlaid on that is the permeability of the membrane to sodium and potassium during the course of the action potential, right? So remember that we have our sodium permeability increasing drastically at this point in the action potential, and that's what's responsible for the rising phase of the action potential. And then we have our potassium permeability increasing kind of part way through the action potential. At the same time, our sodium permeability is decreasing, and those two events together are responsible for the falling phase of the action potential. And then of course we have the after hyperpolarization due to the continued permeability, higher raised permeability of potassium, okay? So these permeability changes are due to the gating properties of our sodium and our potassium channels, okay? So these changes in permeability, or permeability, is due to channels. The changes in permeability are due to the gating, the opening and closing of those channels. And so we have two main players here. We've got voltage-gated sodium channels and voltage-gated potassium channels. And what we're going to do here is take a closer look at the properties of those two channels and see how those properties lead to the permeability changes that we see during the action potential. Okay, so starting with voltage-gated sodium channels, voltage-gated sodium channels have two gates on them, okay? We've got an activation gate that is shown right here in cartoon form, right? So that's what this little black thing is right here, okay? This is the activation gate, and it gets activated by voltage, okay? So it gets activated when the membrane potential rises. What's going to happen is the activation gate will open, okay? Second gate is an inactivation gate, okay? And that's shown here as a little ball, okay? That inactivation gate is voltage independent. It's basically going to close a certain amount of time after the activation gate opens. Okay. Now let's take a look at what happens with this sodium channel over the course of the action potential. Okay, so we're going to start with resting membrane potential. When we are at our resting membrane potential, the activation gate is closed and the inactivation gate is open. So here's a question for you. Take a moment to think about this. In this situation, is there going to be sodium flow through the channel? Yes or no? Okay, hopefully you figured out that there will be no sodium flow through this channel. That's actually indicated here by this sodium kind of bouncing off the ion channel right here. There's no flow through the sodium channel because the activation gate is closed. The pathway through the channel is blocked off, okay? Let's move on through the action potential, okay? So remember the next thing that happens, or kind of the first thing that triggers the action potential, is that we have a depolarizing stimulus come in, okay? When that depolarizing stimulus comes in, that opens the activation gate, okay? And it's that event, or that event, it's that gating that is responsible for the threshold of the action potential. The threshold for the action potential is basically the membrane potential that you have to reach in order to open this activation gate, okay? So once we open the activation gate, what is going to happen? Take a moment to answer that question. All right, hopefully you figured out that once the activation gate is open, we now have a clear path for sodium to cross the membrane. That's what's shown in this figure here. You might remember that sodium will be entering the cell because we started at a negative membrane potential. Sodium wants to be at a positive membrane potential. Remember, its equilibrium potential is plus 60 millivolts. So it is going to move into the cell in order to bring the membrane potential up, okay? So sodium's gonna move into the cell. We are going to get this depolarization. So we're entering the rising phase of our action potential.